So I'm going to be calculating example 13-1 from the book. It's a good way to start solving these problems because you can check your answers. And if you can do this, you should be able to scale it up. So we're looking at doing a two-stage separator calculation. We've got the conditions of the separator, temperature and pressure, the stock tank temperature, atmospheric pressure. We know it's at its bubble point at the reservoir conditions. So what we get at the surface will be a correct separated gas and oil. It's telling us to use K-factors from Appendix A and use decane for the heptanes plus. So here's our fluid. Here's the compositions, or Z of the fluid. Here's the heptanes plus. Here's more properties of the heptanes plus we'll use later. So now we're wanting to calculate producing GR, stock tank oil gravity, oil formation volume factor. So I set up a spreadsheet to do this calculation. It looks something like this. So I basically went through and started cutting pieces of the example problem out and have them stacked up here so we can do this calculation. So we're given the components here. Here's all the components. Here are the tables, the values given for the composition coming out of the well into the separator. We call that Z sub J. So there's all the composition. These K factors I already went through and filled them in, but so you see where I'm getting them from. There's two different ways. Well, I can show here. There's what the K factor chart looks like. Of course, I've copied and pasted it here, but I can show you in the book too if you want. We go back to the appendix, and here's equilibrium ratios. That's butane, propane. So here's the methane chart in the appendix A, 495. So we would come to the separator pressure and the separator temperature is one of these lines, and you can zoom in on the PDF pretty good. Problem is it's really hard to read these numbers. So for the sake of solving this problem, I took the values that he had found from the charts at 114.7 psi. So the separator is at 100 psi. We got to add the 14.7 for atmospheric, 75 F. And here's those values. So this was given in the example problem in the book. So I've gone ahead and entered those in. So now the first thing we want to do is calculate the liquid fraction of this. So we can use this Z and the K factor to find that out. Here's the formula for that. So it's Z divided by this 1 plus the gas fraction of the cut, which we don't know yet. I put a value up here that we'll fill in later as a guess, and there's for the liquid value. So let's start filling in this equation. So you do Z divided by 1 plus this value. We'll go ahead and lock that. So putting the dollar signs in front locks it to that cell. That's going to be times our K value minus 1. Close out our parentheses, and there we got a value. So now we'll copy those down, and Y sub J is a little bit easier. Y sub J is equal to K times the xj. We'll copy those values down. Now, the sums of each of these columns, we're going to start guessing values for our gas composition, and these should come out to equal to 1 if you've guessed the correct value. So let's go ahead and make those sums. Sum of this guy, it already equals 1. That's incorrect, and then I can just copy that over if I want to. There we go. So this one does not equal 1. They both need to equal 1. And that's because we haven't guessed a value for this yet. So if we guess a value of, say, 0.5, which would be halfway in the middle, it goes ahead and solves, and that's not quite the right answer. This is a little more than 1, that's a little less. So let's change it to, say, 0.4. Now it's flipped opposite, so it's somewhere in there. So we can keep guessing, or we can use the solver, which the solver is up here. In what if analysis, we're looking for goal seek. So goal seek. So we need to set which cell we want to set to a specific value. So I want to set this cell to where it equals 1.0, which is what we want to do. And the cell we want to change is this guy. So this is going to keep changing this value until that equals to 1, and hopefully you have your solution. And there we go. So it got them equal to 1. Here's that breakdown of the solution. Now let's look here. If you take this and compare these values to the values that we have down here, you'll see there's a little bit of round off error. That's due to significant digits. So Excel is using more significant digits in solving their problem. That's why this has a 0.001 instead of 0. And that's because this value is 0.491, on and on. Let's round it to 0.492, see what we get. So 0.492, which is the value, if you go look and follow the example problem in the book, that's what he got. Now these values should match. So the liquid composition should be equal to 1 minus the gas. We either got to be a liquid or gas. So that's our first stage. We calculated our x's and our y's. And then we were able to find these. So stage 1 is done here. We took this known coming in, we did the flash vaporization to the separator pressure, we calculated the moles of gas coming out of the separator, the moles of liquid coming out of the separator. Now we need to take this as an input into the stock tank and do the same calculation so that we can get these two values. So if we go back to our spreadsheet, this would be that calculation. So you noticed I already had it auto fill in. The liquid values are what's coming out of the separator. That is what's going into the stock tank. So these values are just copies of those values. And we would have to go back to the tables and look up K factors at a different pressure. So 14.7 psi, or atmospheric pressure. That gives us all new values for K factor. And then we basically need to do the same thing again. I can try to copy it if I want to do that. Actually, let's do it this way. Let's see what happens. If I copy this and paste it over here, it's almost right, except this, I need new values. I can't use that value. I need to drag that over to here. Everything else looks to be acceptable, except it's not summing yet, so I got to do a new iteration. So let's guess here 0.1, for example. 0.1, not quite there. You can keep guessing. We're going to do the goal seek instead. Let's do goal seek. I want to set that to a value of 1.0 by changing this cell. Okay, solved. There it is. 0.1239. And then I would get this value is 1 minus that value. So that calculated those out, except let's check again. Here's the answers from the book. It's a little bit different, and I need to remind myself what the value he had in the book is. Let me go look there a second, just so we can stay consistent with his calculation. So Here's his N2 value, so 0.1234. We got 0.1239, which is virtually the same. There it is. So now our value should match out fairly well with what he's got his out to be, more or less. It's a little bit off. That's just the rounding error that we're going to get. So let's see, 0.8766. So now those values, we just calculated the n values for here and here. So far, so good. So now the next step. So we've got basically the composition of our stock tank liquid right here. And we have this composition of stock tank gas. So now we need to go through and make another calculation. So we can go to the appendix and get the molecular weights for each one of our components, which would be CO2, methane, ethanes, everything, all the compositions of this thing. So now we want to calculate the weight. So the weight of this should be this times the molecular weight. So you can see 0.74, we're following along his tables from the example problem. And we can copy that down. 218 was given as the heptanes plus value. Remember, heptanes plus 218, that was given in the problem. So here's that value. Now we need to sum that. So this would be the summation of the molecular weights. That would be the stock tank oils molecular weight. And then the heptanes plus is just the sum of, or the propanes, that's C3. The propanes plus the same thing, so adding that. So this shows you the added molecular weight of the lighter components. Now we need to calculate these W1 and W2 values so we can go to figure 11.6 and get the density correction for the pseudo liquid densities, because there are only these liquid densities in the back of the book. So if you look in Appendix A, you can find the densities for propanes and heavier. We don't know what these are. That's why you have to use figure 11-6 to fix it. So here's our formula over here for the W1 and W2. So let's go ahead and calculate those. So W1 is equal to the methane concentration divided by the mixture. So that's this guy. And that gives us a percentage. And I already had that formatted to show percentage. You can do that if you're curious. You can do that right here. That turns the percent, turns the percents on and off. So now we need to do this formula. That is equal to the ethane component plus nitrogen. Let me go remind myself of which one it is. Here's nitrogen. Plus the nitrogen component divided by the mixture minus methane minus CO2. So there's that value. So I take these 0.011, 0.31365. I take those W2, 1, 2 values over to figure 11.6. So I've cut that in. So these lines are your W1s. So I cut and pasted these values over here already, so we know what they are. So you take these, you come to this chart. So this is this is almost zero. So we're very close to zero. The W2 is 0.13. It's quite close to zero. So the correction factor, because this is already in the stock tank, the correction factor is quite small because there shouldn't be any real gas in there. So 0.9996, you may not be able to see that, but that's the value that he found when he was working this problem. So 0.9996 gives you that value. Now we're trying to find the liquid density. So you can get these from Appendix A for all the liquids. Let's get the volume. So the volume would be what? Volume would be the density, that would be the weight divided by the density. That'll give you the volume. So that's the volumes of our liquid. Copy this all the way down. We need to add those up. So there's the grand sum of the density. And then I still had the formulas left in here from before. So this is the volume. So the volume, this would be your molecular weight of heptane or propanes plus divided by the volume of the propane plus liquid. That would be your propane plus density. And then we need to correct it. We correct it by multiplying it by that correction factor we found with these W values. So it's a small difference, but there is a difference. It's a little bit less dense because of these lighter fractions that you need to put in there. Now, calculating stock tank gravity, we would just divide the pseudo liquid density at the surface by 62.37, that's water. And then to get the API gravity, we use the API formula, and that will calculate our API gravity. So that's to that point. So now we need to do a few other tasks. It asks us, we've basically gotten the API or specific gravity of the stock tank oil at this point. Now we need to do a few more calculations. One is we wanted the gas oil ratio of the separator and at the stock tank. Those are two important values. So cut and pasted the formulas up here. We can type those out. So let's do the separator first. Separator is 2138 times NG1 is this value times rho stock tank oil. So the rho of our stock tank oil is this guy right here. And then let's divide that by NL1 times NL2 times the molecular weight of the stock tank oil. That should give us our value, 672. Oh, yeah, that's correct. So that's for the separator. Now, for the stock tank, 2138 times NG2 is this guy times rho of the stock tank divided by NL2 times molecular weight of the stock tank, and there's that value, 85.66. And so the combined, that would be your total formation, or your total gas oil ratio would be this plus that, 758. And we can go check those values. Let's check those values with the book. So here's the book values. 672, 86, 758. 672, basically 86, 758 is the answer. So that's our gas-oil ratio. So now, continuing on, after we've got the gas-oil ratio, we need to be able to calculate the the stock tank density, or not the stock tank density. We need to go back and calculate the separator liquid density. What's coming in, that's actually what's coming out of the reservoir, and convert that back to reservoir conditions, which is very important. So if I come here, this is our original concentration coming into the separator. Here's the molecular weights of these things. So we're going to try to find these values. So I can almost copy and paste some of this. I'll see if I can do that. Copy and paste that over here. Something's not quite right. It's the first part of this, and it's supposed to be that. So that fixed that. Copy these down. I've already got values. Here's my molecular weight for the mixture. Why is it angry at this? No, it's correct. So when we have liquid densities, we already know those. We've calculated these. These values have already been input. It's the same calculation as that. And this value, I've already cheated and put it in there, but if you take 6.24, 3.37, we come back over to these tables. You would come here, come look up, you'll find a value. The value, here's the 6-point line, here's the 3.3 something line, and you'll get about 0.9 as that density ratio. At least that's what he's got in the book. So we would hand enter that 0.9, and then that 0.9, we're going to use that over here. We got to calculate our liquid volumes again, and the sum of that. So I can copy this, paste it over here. Actually, I should be able to copy all of these as well. Paste them over here. So our API gravity back there is quite high. It's because none of the gases come out yet. It's fairly light. Because this is what's initially coming in the separator. So our 0.9, this is times our 0.9 times the propane plus density, gives us that value. So now come over here. Now we need to correct this density for pressure and then temperature. So our density value, let me copy that. Copy. Let's go over to this figure. Let me paste just the value so I know the density. So 44.95 is right in here. Here's 45. There's 44.95 is almost 45, and our pressure is 2,620. So it's somewhere. It's somewhere in there. We get a correction factor of we're going to call it around 0.91. That's what he was getting in the book. So 0.91, I'm putting that up here. You can use 0.91. We would add that to this, and then we would come to this chart, 45.866. So here's 45.86, almost 46. The temperature is 220, which is up here, just so you can see where we're getting these values from, more or less. So 4.78 is the value he got. So we take that and subtract off 4.78. That would be our final value. So let's reincorporate that back over here. So our pressure correction would be this value plus that. And then this one would equal to that value minus, this is our temperature correction, minus that value gives us 41.08. Back to the book, he's got 41.09 for his value. So we're right on top of it. And then we can do the formation volume factor, which is this formula. Actually, here's what's from the book. I need to go over there. And there's our molecular weight, 93.75, more or less. So let's calculate the formation volume factor. That's going to equal to this number times our stock tank density. So we got to be careful here. Stock tank density is not this value. It's actually this value is our stock tank density. And then we need to divide this by so the stock tank molecular weight times the corrected reservoir density times NL1 and NL2. So NL1 times NL2. That gives us a value of 1.458, which is the answer to the problem. So we got our formation volume factor. There's only 2 more questions left, and that is the specific gravity of the gases. So that's quite easy to do. We take here's the separator gas values. So separator gas times its molecular weight, that would give this value. We can take that, copy it down. This is the stock tank gas. So we would come to the stock tank gas values, multiply times the molecular weight. We get their values, copy it down, and let's do the sum. Each one of those, sum of this, we can copy that over. Specific gravity would equal to this value divided by 29, which is air. So there's our specific gravity. We can copy this over, copy that over, and we get the specific gravity of the separator gas, stock tank gas, 0.78 and 1.32. I'm trying to think, I may have to just show that. I didn't think I cut those values here. Let's see, yeah, 0.781, 1.32. So that's the full answer of how you get example 13-1. And other problems are quite similar to this for separators. And it's a really good use of Excel modeling